time dilation and length contraction. The postulates of special relativity are 1. The laws of physics are the same in all inertial frames of reference. An inertial frame is a situation where no acceleration is involved. For example, standing still or a car moving at constant velocity. 2. The speed of light in a vacuum, c, is a constant in all inertial frames of reference. Because of this, when an object moves relative to an observer at speeds close to c, time dilation and length contraction can be observed. These effects compensate for the fact that the speed of light is always constant. Time dilation. Santa is travelling at velocity v away from a child who is standing waving him goodbye. One of the presents on the sleigh contains 2 parallel mirrors and a light source. The mirrors are perpendicular to the sleigh's direction of travel. At time t equals 0, a photon reflects off the bottom mirror. In Santa's frame of reference, the sleigh appears to be at rest, and according to him, the photon takes 2x over c to travel up then back down, where x is the distance between the 2 mirrors. In the child's frame, the photon appears to go diagonally upwards and downwards as the sleigh moves forwards. This can only be seen as the sleigh is moving very fast. It has to travel around the world in one night. The vertical component of the apparent velocity of the photon is the square root of c squared minus v squared, so the time to travel up then back is 2x over the square root of c squared minus v squared. This is the same event occurring in 2 different frames of reference, so how is the child's time related to Santa's? We can assume that they are proportional and equate them with a constant that we can call gamma. We can thus find that they are proportional if gamma is equal to 1 over the square root of 1 minus v squared over c squared. Therefore, we find t prime, in this case the time observed by the child, is equal to the time t0 observed by Santa, multiplied by gamma, which depends on the velocity of Santa compared to the speed of light. Note that gamma is always greater than 1. Length contraction. After dropping off a gift, the sleigh is jostled, and the present containing the parallel mirrors tips over so the mirrors are now parallel to the direction of travel. In Santa's frame, the light travels across and back in time ts equal to 2l over c, where l is the distance between the mirrors. In the child's frame, the photon still moves at velocity c, and the sleigh at velocity v. Therefore, the photon appears to be moving relative to the mirror, with velocity c minus v on its way to the other mirror, and c plus v on its way back. So according to the child, the time t prime it took to go forward and back is the length between the mirrors divided by the speed on the way there, plus the length between the mirrors divided by its speed on the way back. We can simplify this to 2 gamma squared L prime over c. We know from what we found out about time dilation before that t prime equals gamma t naught, so we can substitute in these times to see how the lengths are related. We find that L prime equals L naught over gamma. Because gamma is always greater than 1, from time dilation we can see that the child would see the photon return to its original position later than Santa. From length contraction, we see that the child would see the present to be shorter than Santa's measurements. So here's an example question. Muons are fundamental particles with rest mass 200 times greater than an electron. They can be created in the upper atmosphere by cosmic rays and travel at about 0.99998 c with a lifetime of 2 times 10 to the minus 6 seconds. If a muon is created at 50,000 meters from the Earth's surface and travels directly downwards towards the Earth without any collisions, will it reach the Earth before it decays? It is incorrect to say that the muon travels a distance calculated from classical physics. Distance equals velocity times time, so we can find that the muon travels 600 meters, so it would get nowhere near the Earth's surface. This doesn't take relativistic effects into account. We can find the value of gamma for this velocity. It is 158.1. We can use either time dilation or length contraction to solve this problem. To an observer on the ground, the lifetime of the muon appears to have increased by a factor of gamma according to time dilation. T prime, the lifetime of the muon, appears to be equal to 3.162 times 10 to the minus 4 seconds. We can then use classical physics to see how far it would travel. We find the answer to be about 95,000 meters, so the muon can easily reach the Earth's surface. To the muon, it appears that length contraction has occurred, and the distance to the Earth's surface is less than a stationary observer sees by a factor of gamma. The distance according to the muon is thus 316 meters, which is smaller than the distance we calculated it could travel in its lifetime. Thus, it reaches the Earth's surface. Whichever method we used, the same result was found.